lesson 11.5 here, we are going to look at what are called infinite geometric series. Infinite geometric series have an infinite number of terms. They go on forever. Okay, as you can see, these two examples that we're going to do down here labeled A and B, you can see they have dot, 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 dot at the end, meaning they go on forever. Okay, and some infinite geometric series have a sum, and then some of them will not have a sum, or it will not exist. Okay, and this is very key right here to determine if it exists or not. Okay, how do you know if the sum exists? It has to do with r in the geometric series. It must be between -1 and +1. If it is smaller than -1, the sum does not exist. If it's bigger than +1, it does not exist. So it could be -1 or 1, but most of the time, if it exists, it's going to be a fraction in between those two integers. Okay, that's very, very key. And I have that on the reference sheet. Okay, so sum of an infinite geometric series, find the sum if it exists. So first we have to find r to see if it exists. And remember, a couple lessons ago when we talked about geometric series, to find r, just a little review here, you take a term and divide by, I'm going to call it the previous term, meaning the term in front of the one you pick. You can't pick the first one because we don't have a term in front of that. So, for instance, when I find r here, I'm going to pick a term and I'm going to divide by the term in front of it. I am going to pick -12, okay, which is really the third term in that sequence. I'm going to divide by the term in front of it, which is +4. So if you notice, that means that r is equal to -3. If you think back to this that we talked about right here, -3 is not between -1 and +1, so the sum does not exist. So sum doesn't exist, and you need to state that if that's the case. Okay, or there is no sum because r is -3. If you go to the next one, we're going to do a similar type thing. We're going to find r. Okay? So, I am going to take this term, -3/2, which is my second term, and I'm going to divide it by the term in front of it, which is 3. So let's take -3/2 and divide by 3. Now remember the rule. This is like 3/1. So really, I take, if I'm dividing by a fraction, I multiply by the reciprocal. So r would equal, and I'd get -3/6 if I multiply these two fractions, which reduces to -1/2. So there is what r is. You can use your calculator also. Let me just show you that. You take, in parentheses, -3 divided by 2. So take -3/2 and we divide by 3. So divided by 3. So you can see it's -0.5, or convert back to a fraction. And you know that that's -1/2. Okay? So let's go back here. But this is the algebraic way, which when we get to chapter 9 stuff, you need to know algebraic fractions and multiplying by the reciprocal. Now, if the sum exists, so r is, in this case, between there, -1/2 is in there. If it exists, here's the formula that you use. So let me get rid of this. Okay? The sum for an infinite geometric series, if it exists, after you check r, I'm going to put my little infinity symbol down there. I take a1 and I divide by 1 minus r. So sum of an infinite geometric series, notice a1, it existed on this, is 3. And then I take 1 minus r, which is -1/2. So this ends up being +1/2. So it's 1.5 or 3/2. So I have 3 divided by 3/2. If you use the rule, that's like 3/1 divided by 3/2. So I multiply by the reciprocal. 3's cancel, so I get 2 on top over 1, or that's going to equal 2. Now you can use your calculator. 3 divided by 3/2. So if you go there, 3 divided by, and then 3/2. As you can see, it's 2. So I'm just showing you calculator works also, but you kind of need to know the rules. So the sum for this one, your answer would be 2. And the reason is you see that the series alternates signs and those fractions keep getting closer and closer to 0. That's why that one has a sum. If you notice this first one, we got positive 36, then negative 108. I'm not going to list out the next terms, but that one does not have a sum just because that r is negative 3. It's got to be between negative 1 and positive 1. Just some vocab here. You can read these. If you can add up a piece of a sequence, then it's called a partial sum. If you have an infinite geometric series that has a sum, so that would be like this second one that we did here, it's a convergent series. Okay, we just call it it converges to a sum. Okay, just some definitions for you to keep in mind. We can also do segment notation for infinite geometric series. So this is for infinite. Remember, that's the sum. Okay, this is A1. This tells me that this is an infinite geometric series. We're using that sigma symbol, but on top we're going from n equals 1 to infinity. So that tells me it's infinite. Okay, just like in geometric series, the thing that got raised to the n minus 1 power is r. So A1 is 5. R in this case is 1/2. And n is infinite. Okay, so r is equal to 1/2. That tells me the sum exists because it's between negative 1 and 1. So the sum exists, so we're going to use this formula. The sum of this infinite geometric series, and I know this is infinite because of that infinity symbol on the top of my sigma summation symbol, is A1, which is 5, divided by 1 minus 1/2. 1 minus 1/2 is 1/2. So this really means 5 over 1 times I multiply by the reciprocal, which is 2 over 1. 5 over 1 times 2 over 1, or 5 times 2, is 10. There is the sum of that infinite geometric series. So more with segment notation like we've talked about earlier in the unit or the chapter here. And the last thing we're going to look at, how to write a repeating decimal as a fraction. Okay, because it is a rational number. Every repeating decimal is what we call a rational number, or rational ratio means it can be written as a fraction. Okay, we're going to actually look at the process to do that right now. So in this repeating decimal right here, it's 0.25 repeating. That tells me 2 digits repeat. So we're going to multiply by 100 because this is the hundredths place. Remember, it goes tenths, then hundredths. If you had 3 digits repeat, you'd multiply by 1,000. Now, what do I mean by multiply by 100? We're going to let D equal 0.252525, and so on. Okay? Dot, dot, dot. What I'm going to do is, because I have 2 digits repeating, is I'm going to say then 100D, I'm multiplying D by 100. If I multiply this side by 100, that moves my decimal over 2 places. So I have 25.252525, and so on. Okay? So we're going to take these two. I'm actually going to change the order of these a little bit. So I have 100D equals 25.252525, and so on. And right underneath it, I'm going to put D equals 0.252525, and so on. And I'm going to subtract. If you notice what happens when you subtract, everything after the decimal points cancels out. This is 100D minus 1D, which is 90/90. And we're left with 25 here because everything over here canceled out. Well, how do I solve that for D? I divide by 99. So the decimal number, I use D to stand for the decimal number, or fraction in this case, 25 over 99. Now if you actually take your calculator and take 25 and divide by 99, it should end up as 0.25 repeating. And that's how you convert a repeating decimal to a fraction. Now this was an example of multiplying by 100. If you have 3 digits repeat, you multiply by 1,000. If you have 1 digit repeating, you multiply by 10. If you have 4 digits repeating, you multiply by 10,000. Okay, so just an example on that.